Hi, good morning, and welcome to the ZP Developer Zone webinar. We do this webinar once a week, just really to answer questions that come in, technical questions that come in during the week. And it's sometimes just easier to kind of talk through things and illustrate things rather than just kind of emails, etc. So we try to be efficient with people's time, try to give the most illustrated answers we possibly can within the time constraints, because we try to get everything done in the next 30 minutes. So just to say, we do have the ZP Academy. Don't forget there are a couple of free courses on that. We did have a nice anecdote the other day that somebody did a couple of our free courses on the ZP Academy and then also attended our ZP workshop in Horton, so in Norway that is. And we obviously do the webinars. We've got this webinar today. Next week we actually have a webinar on food sense. We have collaborations, definitely looking at recruiting PhDs from at the moment with a couple of UK universities. We make job offers. We've had 2 new starters this week, and we have our ZP Developer Zone website, and as I say, workshops. And workshops, we can sort of do a certain amount of answering in these webinars, but there's a point at which the workshops are over approximately 16 hours worth of learning, so and doing, because we do lab practicals as well. Let me just go forward and say on those workshops, we are having a couple in Horton, in the UK and Norway. There's a general link to the workshops below. If there's not a workshop that's convenient with the times that you want, let us know so that we may be able to schedule a few more workshops. Question number 1 was really about sensors for perfusion, in particular glucose. So I'll be talking about glucose sensors in a flow stream shortly. And we will also be talking about electrodes in 96 microwell format. I will be addressing that in a minute, how to kind of make electrical contact with these kind of electrodes. We also had a customer who is making chloride resilient electrodes. I really encourage people in their first sort of sensor exploration to not go with the chloride resilient electrodes. It takes a lot of optimization, and I'd rather people sort of focus on the working electrode and get a kind of a signal out of their working electrode before they start sort of worrying too much about the reference electrode. But with this company, I think they've been working for quite a long time, and they kind of know that they've got a signal that's in part due to the reference electrode, and so they want to kind of take the reference electrode out of their signal, out of their equation. Somebody's asking about the difference between a lactate. I should sort of put here a generation 1 lactate and a generation 2 lactate sensor, and of course I'll answer that. And then finally, a question has come in. We were having a bit of a chat online about the quality of SPEs, intersheet and intrasheet reproducibility. I'll talk about sort of around SPEs, the problem that people have with SPEs, screen printed electrodes that is, and then how we kind of guarantee our quality. Question number 1, it was quite a long question. So somebody wants to put a CGM in a continuous flow stream and do continuous measurement. That's completely fine. I mean, at ZP, I think, a sort of third of the business is around continuous glucose monitoring. We often do it by putting sensors transdermally, sort of into the skin, but they want to measure between 2 millimoles per liter. Millimoles per liter and 20 millimoles per liter. So that's 20 millimolar and 2 millimolar and 20 millimolar. That's completely fine. That is the clinical range, and they're probably choosing it because they're somehow involved with human health. They want to sample every 20 seconds. I mean, a glucose sensor, it doesn't care what you want to sample at. It's just going to keep on giving you data anyway. So it's just your save rate. So it's often, you can, we might save every second. But it's sort of up to you. But on most kind of clinical applications, once a second is just more than an adequate. But that's what we can do. He doesn't need to be biocompatible or sterile. It's fine. I mean, we do tend to make things. It's quite a lot of effort, but we do work in we are what's called ISO 13485. We do a lot of sensors for human applications, and so we do get involved with making things in an aseptic environment, and also doing cytotoxicity and biocompatibility. They would prefer sensors to run up to 2 weeks. I'll show you that we've got over 6 months worth of data. I think they're worried about this flow rate. I'm not particularly worried about this flow rate. 25 mils per minute it's not fast. I mean, it's, you know, it's all a relative thing, let's say, but I think the sensors would sustain this. And when I think about it, sometimes we test sensors in a beaker, and they're, you know, the kind of shear because of the rotation of the solution in this those beakers can be quite fast as well. Do our sensors have required conditions, e.g. pH and temperature? So most of the data I'll show you today is done at pH 7.2. It's not that we require it, it's just that's where we work at because of human health. So we prefer to be at pH 7.2 because that most of the data then that we have on our website is most relevant. And there is a temperature effect on glucose sensors, but I do have data for that as well. It's also saying here, look, I'm not so interested in the R&D potentiostats. I want to build my own. Understood. I'll also give you a little bit of guidance on that as well. So just to say that I will link to this data as well. This is a CGM, continuous glucose monitoring sensor from Zimmer and Peacock. We're testing it here at 0, 5, 10, 15 and 20. Quick shout out actually, everyone who attends a ZP workshop definitely makes a glucose sensor. So I think that might be a good thing for you. I'm also going to link to this as well, where we're actually testing a glucose sensor in glucose. This is 3 millimolar, and you look at that drift, and the drift is actually following a temperature profile. So we're changing the temperature and watching the glucose signal a change accordingly. So I can see here quite a sort of strong, let's say, glucose response. So I would say yes, we tend it's good to control temperature. It can be quite a variable on a biosensor, especially when you think there's an enzyme involved in them. So we tend to just work at room temperature, and then the longevity or the continuous measurement. You know, we've had glucose sensors running for over 6 months. Glucose oxidase, the enzyme at the heart of all these things, is really robust. I've tried to link to this data. I've also linked to it here. If you look underneath the video on the YouTube channel, you'll find these links, so hopefully that's useful to you. Low cost electronics is fine. If you're much more of an electronics engineer and you don't want to kind of make an R&D instruments, you know, we do single board potentiostats that you can sort of integrate into your own configuration with sort of I2C and UART, etc. So we do have that kind of solution, and I've put a link to that as well. As I say, I think with this kind of question, is everything CGM, everything continuous glucose monitoring in a perfusion system, then please attend one of our workshops. If there's not a workshop at the time that's convenient to you, let me know, and we may be able to call an extra workshop anyway. Let me go forward. Now on to the question number 2. Question number 2 is really about 96 well plates. You'll notice that if this is your question, I do remove, I think, things that I would otherwise, you know, want to anonymize and protect people's kind of ideas, you know. So I do make an effort to do that. So they're interested in the idea of having 96 electrodes that sit in 96 wells, so they can do continuous monitoring. Is it possible to monitor each electrode separately? It is possible to monitor each electrode separately. That's the or each well separately. That's the kind of intention. They ask here about using a multiplexer. I'm not super keen on a multiplexer because a multiplexer is actually sort of, you know, if it does 8 readings, it reads, it goes to the next cell, it reads, it goes to the next cell, it reads, it goes to the next cell. It's okay. I think we would tend to try and do things in parallel. These multiplexers, I'm not sure. They could be about 5,000 euros approximately. Are these electrodes inside these wells reusable? Anything that's wetted in science, whether it's reusable, these electrodes are reusable, but it really depends on what you do with them. So I can't guarantee that you could reuse them. So if you put something in there and it formed a biofilm, and that biofilm really stuck to the electrodes, and the only way to remove the biofilm was to scrape it off, those electrodes are not going to be reusable. So I'm sorry that I can't give you a definitive answer on whether something's reusable, because half the answer is based on the electrodes themselves, and half the answer is based on the science that you're actually doing inside those wells. Somebody who was interested in how we're going to make connection with these. So these boards have connectors on the back side. of the PCB. And something that we haven't designed yet is, so this is sort of a product in maturation, that you need to have what's called pogo pins that come up and make electrical contact with these pins. So for each well, there's a counter working a reference, and on the back side of this, there's then the appropriate pin, or I should say pad rather, which what's called a pogo pin would come up and connect to that. This person has a second question as well, and I will address that second question slightly later on in this presentation as well. But I've linked to our PCB technology here. They were asking about using a multiplexer. And now in a multiplexer, you've essentially got one potentiostat, but it's using a switch and it's going from electrode to electrode to electrode to electrode. At ZP, we're actually developing a true 6-channel potentiostat. So when this becomes available, at the moment we're just doing it to beta testers, and when it becomes truly available, then we're only going to support this potentiostat with that printed circuit board configuration. So I understand that you've got other potentiostats, but it's not something that we're going to necessarily support, because to be honest with you, this is going to be such a low cost parallel potentiostat. It makes economic sense to actually use this guy, and I've put a link also to this as well. As just a side note, the reason we do a lot of parallel work is because we're ISO 13485. We want to get data that's statistically relevant, so therefore we test in parallel, because then we get a lot more data per effort. I mean, it helps us with our statistics. Question number 3: if you're making a biosensor, for maybe a perfusion system where the chloride is constant, then you don't have to worry about this. If you're making a biosensor for testing in bloods, you don't have to worry about this. If you're making a biosensor for testing in interstitial fluid, you don't have to worry about this. But there are some applications, for example, testing urine, where the chloride concentration could be variable, and people who are making biosensors there, they want to put a drop of urine and get a signal, and they may have to work on making their reference electrodes. We sort of call it chloride resilient, but it's a way of really making that silver chloride reference electrode not sensitive to the chloride in the sample. And so we actually have a solution for that. We kind of have a solution that people can buy and they can pipette onto their particular product. So somebody's bought that product, and I realized that we were a little short on information for them. So you get sort of 2 vials in the pack. You decant 300 microliters of the chloride resilient premix. You add 10 microliters of the activation solution, and then you vortex those things together. And once you vortex it, you really want to be using it at that point. Now, what other scientists say is actually add 3 microliters of the solution to that reference electrode, for example. Wait 24 hours. I mean, this is at room temperature, and repeat that actually 3 times. Now that means that's 72 hours. I would describe that as not terribly optimized. I mean, these are just guidances we give people to kind of start with. What I mean by not optimized, to make a reference electrode and have to spend 72 hours doing it, in a real factory, we obviously run factories. You don't want to be doing this, So this is okay starting point. The first line's about decanting the 300 microliters and the 10 microliters. Yeah, that makes this solution. And how you really deposit it and how long you really leave it to cure, I think I've said to them, look, that's something you're going to have to really optimize. Side note, we do have a system called Julie. Julie is a cloud database. We use it all the time. It's going to be relevant to questions in a bit about screen printed electrodes. But Julie allows for data acquisition, data storage, data processing, data visualization. And it also has a little feature called add-ons. And in those add-ons, there's a feature on design of experiment. The reason I say that is whenever you want to really optimize something, you've got lots of, you can just do it sort of by changing some parameters and seeing how signal changes with parameters. For example, in that chloride resilient work I was just trying to describe. But actually you can do a much more sort of structured approach to this, and a design of experiment is a much more structured approach to doing that. Now, question number 4, somebody's asking us about, can you describe the difference between a generation 1 lactate sensor and a generation 2 lactate sensor? So I will answer that question now. And I will answer it by saying we do cover this very thoroughly in a workshop. I mean, you know, and actually people get to test lactate sensors. So if you really want the answer to this, then I would actually attend these workshops, link below. But I know it says glucose here, but just change that word glucose to lactate. And it's the same story that you actually have an electrode in a generation 1. We have an enzyme on there. We have a barrier layer on there. And the glucose, but actually just call it lactate. The mechanism is exactly the same. Gets to the enzyme, and then we have a reaction between the lactate, which I've labeled glucose, with its enzyme, which then produces, in the presence of oxygen, hydrogen peroxide, and that we detect in a generation 1 lactate sensor. So generation 1 lactate sensor suggests that you've got lactate and an enzyme. The enzyme's a peroxidase, an oxidase, and you get a reaction between the lactate and the enzyme, and you get the generation of hydrogen peroxide, and that's what we detect. You know, now if you want, 650 millivolts seems a bit arbitrary. And again, it really is covered in our workshops, and everyone gets to test one of these sensors, and they actually get to test lactate sensors, and they also get to build glucose and test glucose sensors in the workshop, just to contrast it with a generation 2 sensor. So it's going to be a very similar story. So I'll click and talk very quickly. This is a generation 2 glucose sensor, but can also think of this as a generation 1. A generation 2 lactate sensor. So we have, rather than glucose trying to get to that enzyme, we have lactate in this particular question. The lactate again reacts with an enzyme, but this time there's not an oxygen atom. It's actually a mediator. So at ZP and at other companies, we sometimes use mediators, which are really just sort of taking the role of what oxygen would naturally do, but the mediator is helping to shuttle electrons, and it's the mediator, the reduced mediator, that we then detect, and it allows us to do it at a slightly lower voltage, which is argued that it reduces interferences. It's just a slight thing that actually some generation 1 sensors, which you would argue are not as good as some generation 2 sensors, actually have better clinical data. And it's just because sometimes the sort of subtle, the details of this biochemistry, though it would seem that one was better than the other, when you're actually making a complete product and a complete system, one element is not the break of, or is not the determinant of the overall sort of clinical efficiency of that system. It's much more nuanced than that. But generation 2, basically, we've replaced the oxygen with a mediator, and it allows us to reduce the potential at which we then do the final assay. Again, I cover that in a much more detail in our workshops. Question number 5 is a really interesting one. It's been a really bit of a journey for us. But fundamentally, the question is what's your repeatability within a sheet, and what's your repeatability between sheets? So when I say sheets, I'll just basically we make, this is a kind of, I realize this sheet is actually a slightly small sheet. We make sheets of 300 screen printed electrodes, and in order for people to be able to get these electrodes out quite easily, we actually perforate, which means that we kind of half cut them out so people can actually just pop out these electrodes. Now that's a ceramic, that's not what I'm referring to, but I am referring to these PET sheets. And I sort of say it a lot, but actually these are really by far the world's best quality screen printed carbon electrodes. The question is, why do I say that? It's fair enough to challenge it. If you want to get these at really low cost, then this link is underneath the video. They're about 83 cents each, and in some sort of economic zones, that's really a super low cost price and a really high quality product. Now, once upon a time, and this still happens in other companies, that people carry, and we do carry, a really large range of screen printed electrodes. But we changed our minds on this and said this is not good, and we actually tried to sort of encourage everyone to use a much limited set of electrodes. And the reason that we've we do this. I mean, my career on this kind of work goes back, good 23 years. But, also the experience that, at ZP as well is, why did we change? Why did we sort of say to people, stop going for custom electrodes, stop going for lots of strange or unique geometries, and actually everyone use some of our hyper value electrodes. We have a hyper value carbon, a hyper value gold, a hyper value platinum, hyper value graphene. Why are we doing this? Why did we change? Well, it's actually hard to make a repeatable electrode. It seems so trivial. Everyone says, these things are super low cost. Yeah, low cost comes when you're at high volume. It's actually hard to make a repeatable electrode. And I know that's the case because we keep getting inquiries where people say, what's your repeatability? Because they know, that vendors are shipping this kind of stuff and it's not repeatable. So our sort of the mantra when I was thinking about this was, make one and make it well. When you try to make 50 different variants on something, you're essentially splitting the quality effort among the 50. No, make one thing and make it well. That's a sort of, a philosophy. But more importantly, you've got to make a lot of it and you've got to make it regularly. Manufacturing is not something you just turn on and turn off. Manufacturing involves machines, processes, and people. And these machines, processes, and people have got to be in this kind of constant workflow in order that everything is fresh, all the equipment's, is all tuned up. The materials are coming, we're not leaving inks on shelves for months on end. Things are having quite a velocity through. So you've got to make a lot of it and you've got to make it regularly. And that's the problem. When you've got sort of 50 customers on 50 different electrodes, you're basically, splitting the total manufacturing volume among 50 individual products. It's not good. You have to consolidate and everyone essentially get onto the same product so they all get the benefits of scale. Now, I see here, eat at your own restaurant, which is ironic because the video I'm playing here is what makes ZP electrodes pretty good is because actually we understand the fundamental breakage in the screen printed electrode world, which is people are trying to offer too much options, and it's really messing up the volumes and the frequency at which they manufacture. Something else that makes ZP unique is we eat at our own restaurant. And what I mean by we eat at our own restaurant is the biggest consumer of ZP screen printed electrodes. We're absolutely unique among anyone trying to sell screen printed electrodes. We are the biggest users of screen printed electrodes. So who is the first person who would be impacted by quality issues at ZP's screen printed electrodes? Let me think. It's ZP. So therefore, when we sell screen printed electrodes on our web store, we're essentially doing that as a service to the community because we need these electrodes, whether we're selling them or not selling them on the web store, we need them. And the fact is, when you look at like some of the videos that we make, you'll notice that we're not doing a calibration in some of our applications. And the reason being is because we've controlled the manufacturing. So we didn't need... So a lot of reasons why people have to do sort of, especially when you read scientific papers or they normalize signal, it's because they're trying to get rid of manufacturing variability on the underlying electrodes. You'll notice that in some of our videos, we take a screen printed electrode, we prepare the sample, we put it on, we get a result because we're making very repeatable electrodes. Now let me go forward, and it's because we, like our customers, are all using the same electrodes. So we do eat at our own restaurant. And before our customers know there's a problem, we know there's a problem because actually we're the ones using these. Now our workflow is this. We do manufacturing. We call it IQC at this point, which is incoming quality control, because essentially we're manufacturing and then we want to bring those electrodes into our sort of systems. And so we do an IQC on the way. And we have a process, and we have a cloud system called Julie, which allows us to process a lot of data. So let me go forward with, everyone does visual inspection. It's not that hard. At ZP we do it. Make sure that anything that's sort of gross is obviously rejected. But something that we do, people say that they do electrochemical testing of their screen printed electrodes. They may do it. I don't think they're actually tracking it the way we're doing it. I definitely know that they're not using the kind of statistical tools that we're using. And I know that they're not sort of having historical data that we're doing, but what we're doing is, every time we make electrodes, I'll describe what's called wafer mapping in a minute. We're basically taking samples and testing them and making sure that anything obvious is rejected, but we're a bit more subtle than that. And we also do this to our biosensors as well. So when people order biosensors off us, we've always done a test to make sure that these things actually work before they go out. Let me go forward a little bit. That's a glucose sensor being tested, and that's Julie doing the analysis. Yeah, we do something called wafer mapping, where we'll have several sheets, and we'll test the sort of the beginning, middle, and end. And each sheet basically has coordinates. We have rows and columns, and I say here we'll do a quick demo, but let me just bring this up very quickly. This is Julie. Julie is a data management system designed specifically for electrochemical data that we have at ZP. What I will do here is say that what I can see here is that one of our operators, what I can see here is these numbers 12.1, 1.25, 1.13, they tell us what row and what column we're actually looking at. And then they will have selected, or they will have tested electrodes from different rows, different columns. They upload the data, and then Julie is able to, we're able to say, look in this space here, find the peaks, look in this space here and find the peaks. So we're actually gathering, we can easily gather like 150 data points off a batch of electrodes. And then what makes us, people can't do this because they don't have the tools. And then we can actually just upload all the data and say, okay, look for the peaks, and then actually tell us essentially tell us the heights of those peaks. And then what it allows us to then do is actually then do a sort of statistical analysis on that data and find out what our relative standard deviation is. We also have pass criteria as well. So the reason I know that nothing gets shipped unless it goes through a pass criteria for us, we're looking at peak position, we're looking at peak height. So we always test in the same way. We look at peak height and peak position. So it doesn't matter where the sheet is, it's got to pass this sort of pass criteria. And then what we know is that within a sheet, our relative standard deviation is actually 5%. And this, I just think, is far better than any other screen printed electrode that's made available to the R&D market. But you do have to understand something, that ZP is testing these electrodes for ourselves. If people want to have a kind of quality agreement with ZP about what we're going to ship to them, that's not just going to the web store. We put them on the web store, we say, buy them and try them. They're 83 cents each, go ahead. But we're testing them for ourselves, and whether that testing is relevant to you is a different matter. So if we test by cyclovoltammetry, it means that we've probably got some relevance to somebody who's also testing, whose assay is maybe cyclovoltammetry. But if their assay is differential pulse voltammetry, then what we're doing in our factory is not necessarily as applicable or useful for them, because they're doing differential pulse voltammetry or square wave voltammetry. So it's really a project, an ongoing agreement, an ongoing financial agreement. If people want us to sort of make electrodes, test them in the way that they're going to use them and ship them. Otherwise, they can bypass all of that kind of company interaction and the various costs and just buy them off the web store. But just know that we make them for ourselves and we offer them on the web store then as a sort of service. But whether the standard deviation, the way we measure it, between sheets and within a sheet, is applicable to you, that's not something we're saying, because we would have to test them in the electrodes in exactly the way that you were otherwise intending to use them. But we do a lot of testing. We do sheet testing, and within sheet testing, and we can process the data very quickly. So question number one was, those glucose sensors in that 25 mils per minute, you should be fine. The 96 well, you can connect to each well separately through what's called pogo pins on the backside. And we do have a parallel potentiostat. chloride resilient electrodes. I hope I've described the way that we would, how do I say, how have I described the way we would make a chloride resilient electrode. Difference between a lactate, a generation 1 lactate sensor, generation 2 lactate sensor. Generation 1 uses oxygen as the mediator, generation 2 uses a artificial mediator put in there by the sensor manufacturer. And then the quality of our SPEs, we find that our standard deviation within a sheet or intra sheet is 5%, and our relative standard deviation between sheets is also 5%. And we do actually have pass criteria based on height and peak separation. So, but we are doing that for ourselves. That's an internal thing to keep the quality where we need it to be. Whether that then translates into somebody who's using square wave voltammetry or differential pulse voltammetry, if you want that kind of guarantee, that is actually a project. Otherwise, you can just buy and try off the website. So I want to say thank you very much. If you have any questions of ZP, and I've been having some more questions come in even today. Somebody's asking about the resistance per square of some inks and whether it's too high. The answer is yes, but I'll deal with that next week in our webinars. So thanks very much. Have a good week. I'm going to jump in a car and get myself to some meetings. Okay, thanks very much.